There are different categories of the jet fuel depending on aircraft engines. We can have internal combustion piston engines, we can have turbine engines. For internal combustion piston engines, type of the fuel used is avgas, and for turbine engines, type of the fuel used is jet fuel. However, there are different subcategories of the jet fuel, and the one most commonly used is Jet A1. Jet A1 fuel is mainly made from the kerosene, and Jet A1 fuel is very efficient because it produces high power output with relatively low consumption rate. The second type of the jet fuel is Jet B. Jet B fuel is mainly made from the naphtha kerosene, and Jet B fuel is efficient and low temperatures, and Jet B fuel is very highly ignitable, and its handling characteristic is dangerous. One common characteristic of the aviation fuel is the octane rating. Octane rating of an aviation fuel is the anti-knock power of the fluid. To understand the importance of octane rating, we must know what detonation is. Detonation occurs when fuel is not burned in a progressive manner. So detonation causes engine noise, it causes engine damage, and the power output of the engine significantly lowers. As much as the octane rating of aviation fuel is high, it has more and more resistance against the detonation. Unfortunately, Jet A1 fuel has a very high octane rating, so chance of detonation in Jet A1 fuel is significantly lowered and rarely seen. Fuel is stored in an aircraft in the fuel tanks. In Boeing 737 Classics, we have 3 fuel tanks, and they are the fuel tank number 1, Satan tank, and fuel tank number 2. Fuel tank number 1 is in the internal structure of the left wing, and center tank is in the fuselage in the center sections of the left wing and the right wing, and fuel tank number 2 is in the internal structure of the right wing. A pressure fueling station is located in the right wing leading edge. A fueling receptacle allows a hose to be connected for the refueling. 3 shutter valves allows the fuel distribution to the tanks via the fueling manifold. Such tanks are located at outboard of each fuel tank. Any overflow from the main tanks are collected in the such tanks. Drain lines in the such tanks allows the fuel to drain in the center tank, but does not allow fuel from center tank to drain in the such tank. Each such tank has a capacity of approximately 30 US gallon. A fuel vent scope is located outboard of each wing lower surface. The vent scope provides positive pressure during the flight and also discharges the fuel overboard if excess fuel is collected in the such tank. Scopes are designed to prevent ice accumulation. It's very important to know that we should supply the fuel from the tanks to the engines under positive pressure. So to accomplish this, there are fuel pumps installed inside of the tanks to pump the fuel under positive pressure to the engines, and these fuel pumps are called fuel boost pumps. We have 2 fuel boost pumps and fuel tank number 1, and we have two fuel boost pumps in the center tank and 2 fuel boost pumps and tank number 2. In tank number 1, the fuel boost pumps are labeled as forward and aft. The forward fuel boost pump is attached to the forward spar of the wing, and the aft fuel boost pump is located in a dry bay inside of the tank. These fuel boost pumps are all AC motor driven, so we have the switches to control the operation of these fuel boost pumps in the overhead panel in the cockpit. Adjacent to each switch we have a low pressure light. When the switch is turned on and if the low pressure light gets off, this is an insurance for the pilot that the output pressure of the fuel boost pump is sufficient. The fuel boost pumps in tank number 1 output pressure should pass through a check valve. So the check valve opens at approximately 12 psi. Same arrangement in the fuel tank number 2. In the center tank we have also two fuel boost pumps which are labeled left and right. The left fuel boost pump is installed inside of a dry bay inside of the tank, and the right fuel boost pump is also in the inside of a dry bay inside of the fuel tank. The difference between the fuel boost pumps of tank number 1, tank number 2 and center tank is that the check valves of the fuel boost pumps in the center tank open at relatively low pressure, which is around 1.3 psi. This arrangement is because in normal operations, as long as we have 4 tank fuel or fuel in all 3 tanks, all boost pump switches should be turned on. In this configuration, the fuel is first burned or used from the center tank, and once the fuel in the center tank gets empty, then automatically fuel from the left tank will be supplied to the left engine, and fuel from the right tank will be supplied to the right engine. This is because we need the fuselage to be lighter and the wings to be heavier, not to bring undue stress on the attachment bolts of the wings to the fuselage. Before entering to the engine, fuel must pass through the engine fuel shutter valve. Engine fuel shutter valve is DC powered. It opens when engine start lever is moved to the idle and closes when engine start lever is moved to cutoff or engine fire switch is pulled. An engine driven fuel pump is attached to the engine gearbox and has the ability to draw fuel directly from the tank if both fuel tank booster pumps fail. And the engine driven fuel pump has 2 stages, in low pressure stage and high pressure stage. Between these 2 stages there is a filter. Fuel from output of the fuel boost pumps enter to the first stage of the engine driven fuel pump, which is the low pressure stage, and then it passes through a filter and enters to the high stage of the engine driven fuel pump, and then output of the fuel from the high stage of the engine driven fuel pump enters to the engine, and the first unit which receives the fuel is the MEC or main engine control. A fuel temperature sensor is located in the fuel tank number 1 that senses the fuel temperature and displays the result in degrees centigrades and the fuel temperature indicator at overhead panel. The fuel pump's location and function in the number 2 tank is the same as number 1 tank, with the exception that number 2 tank does not include fuel temperature sensor. If for any reason any fuel boost pump circuit breaker trips during the flight, crew is not allowed to reset the circuit breaker since it may cause fire in the fuel tank. There are maximum and minimum fuel temperatures that the crew should observe during the flight. The maximum operational fuel temperature is plus 49 degrees Celsius, and the minimum operational fuel temperature is minus 45 degrees Celsius. A question comes that what happens if the fuel temperature gets lower than the minimum? In this case, ice crystals start to form in the fuel, and these ice crystals may clog or block the fuel filter. Once the fuel filter is blocked, there is a bypass valve which bypasses the fuel from the filter, and unfiltered fuel will enter to the engine. A light in the overhead panel will illuminate, which will be an indication for the pilot that respective engine is now receiving unfiltered fuel. When the engine is receiving unfiltered fuel, we should expect some rough operations of the engine, maybe flame out, power loss, and some worse conditions, even engine failure during the flight. The minimum fuel temperature during the flight should always be kept 3 degrees Celsius above the minimum limit, which is minus 45 degrees centigrades. There is a crossfeed valve which is a DC motor operated from the hot battery bus, which divides the fueling system into the left in right manifolds. In-flight transfer of the fuel from one tank to another in case of fuel imbalance is not possible because the fuel transfer valve or the manual defueling valve which connects the tanks to the fueling manifold cannot be controlled from the cockpit. To transfer the fuel from one tank to another, the aircraft should be on the ground and the manual defueling valve should be opened manually. However, any condition of fuel imbalance during the flight can be corrected to let one tank feed the fuel to both engines. To let main tank number 1 to feed fuel to both engines, for example, transfer valve should be open and both main tank number 2 fuel boost pumps should be turned off and vice versa. The maximum amount of the fuel that can be loaded depends to the fuel density and outside temperature. A fuel density is considered to be around 0.8 kilograms per liter. We can load maximum of 4,555 kilograms in each main tanks, number 1 and number 2, and 7,029 kilograms in the center tank. In this way, the total amount of the fuel that we can load will be 16,139 kilograms. The main tanks number 1 and 2 must be scheduled to be full if center tank contains more than 453 kilograms of the fuel. Main tank number 1 and 2 can be pressure refueled, or if fuel truck cannot provide pressure, they can manually be refueled from the ports located over the wing. However, center tank cannot be manually refueled, and the only possibility to refuel the center tank will be to transfer the fuel from main tanks number 1 and 2 into the center tank. If there is no AC power available in the aircraft and EPU is also inoperative, ground personnel can still refuel the aircraft by turning on the battery and placing the standby power switch to battery position. This way, the entire fueling valves and gauges will be powered via the battery. If both AC and DC powers are not available, ground personnel can manually open the tank shutoff valves to let the fuel flow to the respective tank. Once required fuel to the respective tank is loaded, the valve can manually be closed. The normal and standard fuel truck nozzle pressure which refuels the aircraft should not be less than 50 psi, which will supply around 1,136 liters per minute to the tank. There are some problems that we may encounter during the flight associated with the fueling system. As an example, fuel cross-feed valve failure. If the cross-feed valve fails in closed position and cannot be opened by its respective switch in the cockpit, each tank will be kept connected to its respective engine and pilot loses the ability to let any tank feed fuel to any engine. In case of fuel imbalance, the only possibility to balance the fuel will be to increase the thrust on engine with high fuel quantity and decrease the power on engine with lower fuel quantity until the tank's balances. If a fuel filter is saturated by dirt or ice crystals, the fuel filter bypass mechanism will bypass the fuel and unfiltered fuel will be fed to the respective engine. If only one engine fuel filter bypass light has eliminated, flight can be continued to the destination, but the pilot should expect, as we mentioned before, some rough operations of the engine, power loss, flame out, and in some worst cases, engine failure and shutdown. But in a worst scenario, if both engines filter bypass lights illuminate, this is a clear indication that both engines are now receiving unfiltered fuel. So this condition, the pilots cannot continue the flight to the destination, and as soon as possible the flight should be diverted and land in one of the suitable airport and nearby suitable airport. A common problem occurring in the fuel system is a fuel leakage. A fuel leakage is suspected if a fuel tank quantity decreases rapidly. There might be a leakage in the fuel tank structure or the engine. An engine fuel leak can be confirmed by visually inspecting the engine, and if a white spray of fuel is observed, there will not remain any doubt that the leakage is in the engine. Engine fuel leakage increases the possibility of engine fire, and besides, fuel will be wasted. The engine having fuel leakage should be planned to shut down, and the flight should be diverted to one of the most suitable airports or alternate airports. Another common problem associated with the fuel system is the fuel boost pump failure. If one boost pump fails in a fuel tank, the second boost pump will normally supply fuel to the engines, and that's not a major problem. But what happens if both fuel boost pumps fail in a tank? If a fuel boost pump fail in tank number 1 or tank number 2, the engine driven fuel pump will suck or withdraw the fuel from the engine, but at high altitudes this will create a problem. And the problem is that at higher altitudes, due to low pressure, air bulbs are released from the fuel, so these air bulbs will clog the fuel lines, and chance of the power failure or chance of the flame out is significantly increased. But the scenario is something different if both fuel boost pumps fail in the center tank. So if in the center tank both fuel boost pumps fail, now there will not be any chance to use the remaining fuel in the center tank. So in this case, the pilot should immediately have an evaluation of the remaining fuel, because the fuel in the center tank will not be used, and we should have an evaluation that if the remaining fuel in fuel tank number 1 and fuel tank number 2 can let us to fly to the destination or not. If not, diversion should be made, and landing should be made in one of the suitable airports. During the flight, in mostly and long-range flights in cold climates, chance of the fuel temperature to become lower than the minimum limit, which is minus 45 degrees Celsius, is greatly increased. As we know, operationally we should have the minimum fuel temperature at least 3 degrees Celsius above the minimum. But if we cannot do this, in order to prevent the formation of the ice crystals in the fuel, there are some ways that the pilots should follow. The first one, they can descend to lower altitudes where the warmer temperature will keep the fuel warm, or if it is not possible, they can divert to some other areas where the warm air is available. And if these two scenarios are not available, the last one can be to increase the speed. It is best to know that that will increase approximately 0.5 to 0.7 degrees Celsius for each 0.01 Mach increase in speed. So colleagues, we had a rough summary of the fueling system in Boeing 737 Classics, and thanks much for being with me in this video, and please leave your comments in the comment box, and or if you have any questions and time available, I will read and answer all those questions to you. Thank you very much, and hope to see you soon in my next videos. Thank you.